In this week's videos, we are going to look at the topic of how we can write a platform driver. Now, this is actually a sort of incremental improvement over what we have already done in the previous week, where we sort of demonstrated the use of a platform driver. And what I mean by that is something where you can just pretty much use the DTS or the device tree specification and the device tree block correspondingly in order to give all the details to the system, right, or the kernel about where a particular peripheral is present, right. And what we saw was in the previous week we had seen that I can of course write a module where I directly specify a physical address when I am loading the module into memory, and the kernel just loads that particular module into memory and then goes and accesses it without needing to know anything further about it. This is fine, except that it is not very portable. I need to know the physical address each time. I need to sort of hard code that into the boot scripts and so on. And as we discussed in the previous week, the whole point of the device tree was to sort of abstract that out, right? So we get this difference where we essentially say, okay, there is a kernel which is very generic, there's a module which is also generic, and how do I tie the two together? Because after all, when I try loading the module into the kernel, I need to give it some additional information such as where exactly is this piece of hardware connected on the hardware or on the bus that is attached to the CPU, right? And that essentially was the job of the device tree specification. And what we saw was by writing the device tree specification, we can then sort of enable a driver which will pick up that information from the kernel itself and load into the appropriate place. And we don't need to specify this information about the addresses as a separate script. Now, of course, it's not like the problem is completely solved because someone still has to write a device tree specification, right? But the advantage over here is, let's say I'm creating a new board, a new system. I only have to go and modify the device tree specification. I don't need to go and recompile or rebuild the entire kernel. I might choose to do that for other reasons such as efficiency or having the right kind of drivers in certain cases. But in general, it is possible to make much more rapid iterations and changes without having to go and recompile the entire kernel. So in this set of videos, we are going to look a little deeper into the idea of a platform driver, right? How exactly does a platform driver find out about where it should bind, and some basic information about the kinds of APIs that are provided by the kernel to help us write such platform drivers. Okay, so the goals of this set of videos is basically to understand how Linux binds a driver to a device. Now, we assume that the device has been provided under the DT, the device tree, right? And that essentially means that it is connected at some place in the platform bus. It might be the AXI bus or something like that, but somewhere in that device tree, the hardware unit has been connected. That in turn has been specified using the DTS, the device tree specification. And what I want is that when the Linux OS or the kernel boots up, it should be able to identify and load the appropriate driver. What we are going to do is to implement a minimal driver, right, sort of continuing with our smart timer example, and use a very simple sysfs, right, the /sys file system based approach for demonstration. I'll also talk very briefly about other approaches that can be used for transferring data into a device, right, but those are more advanced topics. We'll talk a little bit more about them at some later point, right. So there are a few concepts that we need to keep in mind, right. First of all, the thing is we are building what we call a platform, right. A platform device in general is something which consists of all the peripherals which are there on a given system on chip, right. And in general, what we are talking about over here is something which is described by the device tree, right, or in the case of x86 it would be the ACPI, the advanced configuration and power interface, right. But these are in general not discoverable through other buses. So as I already mentioned, there are other buses like PCI and USB, especially for the personal computer platform, right, the laptops and desktops that we are all used to. The PCI and USB buses are actually very powerful extensions of the idea of a bus, which allows so-called self-enumeration. When I take a new device and connect it over there, it actually provides certain information to the system, and the operating system can then sort of dynamically figure out what driver is required and load it at that point, right. And this is actually a very useful way of approaching the problem, very powerful, also quite complicated, right? When we are talking about the platform based design, we usually have a lot more control over what goes into our system on chip. So for example, let's say that I'm designing something for a Raspberry Pi based system. I pretty much have complete control over the kind of things that are attached to it, right? So rather than going for a very generic kind of bus like PCI or USB, well, USB still exists, but PCI, for example, may not directly be supported in the Raspberry Pi. At least most of the peripherals that we want to connect, we would prefer that they get connected in known places directly on the bus. And when we are designing the SoC, we want to keep that bus relatively simple. So we use the AXI bus. Right? Now, what we do and what we saw in the previous videos was that there is this notion of what we call a compatible term, right, which we specify in the device tree. So when we give the device tree specification, we give some information to the kernel saying what kind of drivers is this device compatible with. Now, why is that useful? Because it's just a string, right? It's a matching string that can be used by the drivers themselves. The good part about it is it means that if I want to, I could write a driver for some other device even though I'm not the person who actually built it, as long as I know what is the compatibility string that will be used in the device tree specification, right? And by doing so, what ends up happening is that when the kernel actually tries to search for a driver, I could make it such that my driver is the one to be found. Alternatively, I could also use a slightly different approach where I go and modify just the device tree specification. I don't have to change the hardware, I don't have to change the kernel. I change the device tree specification in such a way that it changes the compatibility string so that it matches with whatever I write in my driver. Right? So as we saw, there are a few alternatives that are present for the entire idea of a device tree and this platform bus approach. PCI and USB are the ones that you are probably most familiar with. USB is probably the one that you have interacted with the most because we tend to carry around USB drives. We use USB to connect phones, various other kinds of devices, right, that just need, there are for example headphones and various other things that are connected on the USB bus, right. It's a very powerful bus in the sense that it has a lot of flexibility built into it, right. The hardware is discoverable, meaning that when you plug in the hardware, there is a basic level of electronic handshaking that happens, which allows the hardware system itself, the bus interface, to sort of identify what kind of device is being connected to it. It passes that information over to the operating system, which then takes over and does a lot more complicated work. We are not going to be looking into this part of it at all now. Okay. The other thing is this platform based approach that I am going to be discussing in this set or in this video is one way of writing drivers for a device. There are others, including what is called the user space IO, right? And there are certain advantages to writing drivers using those kind of approaches, right? Apart from that, there are somewhat more specialized client drivers for certain kinds of devices that are typically very common on most SoCs, and those include things like SPI, I2C, pulse width modulation, general purpose IO, and so on, right? So all of these are typically found on most systems on chip, which means that very often you will find that the kernel actually has built-in platform-based drivers for all of these. So just a recap, right, as we already saw, in the device tree, what we do is we provide a binding, and effectively what we are saying is I have a device which I am going to give it this name smart timer. I also specify what it is compatible with, right, and this string over here, the Acme smart timer V1, is something that's entirely in my control. For example, this Acme is just a generic term that is very often used in computing, right, to indicate sort of, you know, an unknown company, right. So it's sort of a joke from a long ago, but on the other hand, it's now commonly used in order to just indicate the name of a company where you don't want to specify the name of an actual company, right. So Acme is sort of normally would be the name of the manufacturer. So let's say that this is a particular timer or a particular device being built by a company like Cadence, then they would probably have CDNS or something like that in that compatibility script to indicate their code. There could be something like Samsung, there could be other kinds of things which are basically vendor specific. It also has something about the string contains something about the device itself, and it also usually has a version number that's simply to make it sort of easier to sort of switch between different versions of the driver that we might have, right. Now all of that, as I said, is useful only because when the kernel is looking for drivers, it has this information from the device tree. It will go query all the different drivers that it sees and try to find out which ones show that they potentially match with this string. And if it finds a match, then it will try and load that driver and see if that driver is able to communicate with the peripheral that has been marked over here. Right. Now, the most important information in some sense is this register information, right? So, for example, I could have the information saying what is the base address and what is the size, the window size corresponding to a particular peripheral, right? This is something which is actually quite a nice way of presenting information, because what it means is that I could potentially have two different smart timer peripherals, right, each of which is registered at a different address, different base address, right, and the kernel could potentially go and load both of them and identify that it has multiple different things that it can talk to, right. So multiple timers could be incorporated into the system, for example, right. This information, the base address has to be some kind of an address. The second number over here, the expectation is that it is a regular 32-bit value, which is sort of the number of registers that are present over here, right. But yeah, and ideally, of course, what we want is at least this number should match with the actual address space that the hardware corresponding to this peripheral is going to decode. Now, it is possible that I write a hardware module which does not really map onto this entire address space. It is actually only looking for maybe 4 addresses or 8 addresses or something like that, right? A bunch of addresses starting from this offset. But it doesn't matter. What I'm doing is I'm sort of reserving this entire space, and the kernel then knows that nothing else is supposed to be connected out here. Now, all of this is in the device tree specification. I also correspondingly need a piece of C code, but this is not built into the kernel, right? What I do is I put it into the module that I am building. Now, once again, just to remind you, the idea behind modules is that after all, my kernel itself is an ELF file, right? It is an executable that is created, which gets loaded into a certain location in memory and runs, right? Once I point the program counter at it, it basically runs like any other program that's going to run on the system. Now, programs internally tend to call functions, right? And all that we are doing is we are saying that there has to be some way by which I can add a few more functions which did not exist when the kernel was being created. That's the whole idea behind a module, right? So what I do is I write a few functions of my own, such as module register, module probe, and so on, right? Or there are a few standard names that are used for that, and I register those with the kernel by giving it some information in another file, an object file, right, which would normally be called a .o file, because after all we know that when we take a .c file and we compile it, we get a .o, an object file. In the case of the kernel, it's a more specialized kind of file. It's called a .ko file, a kernel object, right? And the kernel, when it sees a .ko file, knows where to put it. In other words, it also is able to interpret it as an ELF format file, right, an object file, load it into some location in memory, and then pick up those things. What are the parts that need to be registered as part of the kernel, and do the appropriate entries in some lookup table that it manages internally. So in our case, what we need is that the module code that we write will have some kind of a struct which basically gives this information about the device ID and so on. And within that, there will be one entry. After all, this is a struct. So this syntax that you see over here is, I am initializing a struct. In fact, if you look at it, this syntax basically says that this is an array of structs, right? And what this is saying is that what we have within this first set of curly brackets is the first struct within that array, right? What does the struct itself contain? It has one element which is compatible, which is probably declared as a char star or something of that sort, right, or a string of some kind, and I initialize it with this value. That's the only part of the struct that I am initializing. The next thing that you can see is I also have one empty struct over here that is used in order to indicate to this array that it's the end of the array. So you would recall from the basic C programming course that this is one way by which I can initialize arrays. So in other words, there's nothing kernel specific about this. I'm just sort of initializing an array of structs using whatever programming techniques the C programming language allows me to use. Okay. So now what happens over here is, as and when the kernel loads up, it then it picks up this device tree specification, but not as a DTS file that has been compiled into something called a DTB file, a device tree blob. And it creates a device corresponding to that, and usually depending on the way the kernel has been set up, there is something called event, right, a U event, a user space event, which is emitted by the kernel. Now what exactly does that mean? Right now we are not going to go into the details of that. What it means is that the kernel has some way by which it can communicate with different functions or programs that are looking for certain kinds of information, right? So the kernel needs to be able to manage multiple different processes. Some of those processes might be interested in responding if certain kinds of events occur. And the kernel, after all, it's what has control over your entire system, manages this whole business of sort of communicating between these different blocks. So it can emit an event with a certain string out there, and in user space there is some part which basically says, okay, match whatever is this compatible string with whatever came out of that U event, and then call this function called mod probe in order to load the appropriate module. Okay, and we'll look at an example of how we can automatically probe for different modules and load them, right, later on. So one thing you might have noticed over here is, you have this OF_OF, right, and it's not very clear what that is. It turns out that actually stands for something called open firmware, right. It's essentially more or less a synonym for the device tree. It is just a different way by which the thing was described earlier. So when we have this struct OF device ID, it is a standard type definition that is used inside Linux, inside the kernel, which provides the match table for drivers, right, and it basically contains these strings, the compatible strings, which tell you what kind of things the driver supports. After all, this OF device ID is something that is coming inside your C code, your module. The compatible strings you need to provide, saying which hardware modules are you compatible with. The kernel then looks at the device tree, finds out a suitable match, and it matches the device tree nodes to drivers at runtime. Okay, so this OF_ approach is used on any architecture with the device tree, right. For example, that includes ARM and other kinds of architectures such as, well, the most common one that you are likely to see nowadays is RISC-V. There are others such as PowerPC, MIPS and so on, which also exist and which use the same device tree based approach. Just to clarify, right, ACPI is used by the PC or the x86 based systems, right. They don't use the device tree, they use ACPI instead. But there is a very similar, just like we have OF device ID, we have something called ACPI device ID. There is also the PCI bus which uses a PCI device ID. In other words, it should be clear at this point, right, that what we are trying to do is to come up with a generic solution for a problem. What is the problem we are trying to solve? I want my kernel to just stick to the bare minimum, right. I want it to have something which will boot up on any system with this particular processor, right, and is not going to sort of hang if a particular peripheral is present or not present, right. But at the same time, if there are certain peripherals that are present, I want to be able to identify them and load drivers for them. And the solution that has been identified for this is, I need to provide some way by which the hardware can be specified to the kernel. The driver can contain what kind, some kind of a string or a specification which says what kind of hardware it is compatible with, and the kernel should be able to sort of map between the two. Depending on the type of bus that you use, right, you might either use a device tree or you might use ACPI or you might use PCI. There are different techniques by which the appropriate drivers can get loaded in.